We owe our current understanding of homeostasis in large part to five scientists, and following the chain of their discoveries will help us to break down what we know and don't know about adaptation. So Claude Bernard, pictured left, studied heat regulation and eventually developed the idea of a milieu interior, that the internal organs of complex animals exist in an environment impervious to the outside environment, and that milieu had to be managed through perfectly matching that outside environment in opposing ways. Walter Cannon, pictured right, evolved this idea initially by studying the gut and the regulation of digestion. He realized in his lab work that a chemical, later known as adrenaline, had a similar effect on the gut as fear, and he came to develop what we now know as the fight or flight response. As a field doctor in World War II, he dealt with trauma and the body's attempt to recover from shock. And combining Bernard's work with his experience, he developed the concept of homeostasis. The word homeo, meaning like or resembling, was chosen instead of homo, the same, to signify that there wasn't one environment or milieu, but a range of safe values for a cell or organ system that the body would try to maintain. There are also different milieus within the body. And he developed 6 principles for understanding this new homeostasis. The first was essentially a restatement of Bernard's. The later ones were interesting. He included the idea of change factors, chemical, physical, and nervous regulators that responded to that environment. There could be many factors, not just 2 in a given situation, and each factor would move certain targets in one direction. So blood pH, temperature, CO2 levels, and it would aim to move it towards homeostasis. The body would maintain that homeostasis by turning up one set of factors and turning down another. So if you find in the body a factor, some chemical or enzyme or hormone that changes blood pH or temperature in one direction, you're pretty much guaranteed to find something else in the body that moves those variables in the opposite direction to keep the body in line. Arthur Rosenbluth and Norbert Wiener were among the first to investigate the new field of cybernetics, and they applied the engineering concept of negative feedback, a central regulator that notes deviation from a value and applies effects, so these control factors, to bring it back to baseline. They also developed the idea of predictive feedback based on a signal, that even if the body was not out of a normal range yet, a complex system can measure changes in values as they're beginning and start compensating early, and that it could also adjust to certain states. So, for instance, the new model better explained how the body keeps a completely different milieu of heart rate, blood pressure, and ventilation rate during sleep than while you're awake. And finally, we come to Hans Selye. A researcher into chronic disease and stress in animal models, Selye followed Cannon's discoveries and connected it to his observations of animals. In a wide range of diseases, which looked very different on the surface, Selye noticed some subtle issues that were present in all of them. This finding led to the general adaptation syndrome, and it's essentially this. A stimulus attempts to move the body from homeostasis and is met by a specific reaction. For instance, increased heart rate and blood to the extremities when we're training. If a stimulus exceeds the ability of that specific defense reaction to handle, it becomes a stress. And stress triggers a general stress response, which mobilizes extra body resources to handle that threat. The interaction of the type of stimulus, the specific defense, and the general defense creates the appearance of a variety of stress illnesses that really come from the same thing. This general adaptation syndrome had a pattern. There was the alarm phase, the initial response, where the body mobilizes resources against the stress. There's the resistance phase, where the body returns to baseline and the markers of the alarm phase begin to decrease. And then finally, the exhaustion phase, when the general adaptation syndrome, the general response, fails to handle the stress, the organism begins to see those alarm markers again. So if blood pressure, for instance, were to pick up in the alarm phase dramatically, and it was begin to lower in the resistance phase, but yet the stress was too great or sustained for too long, and the organism started going into exhaustion, you would see that blood pressure rising again. In 1960, Fred Wilt took one of these ideas, Hans Selye's idea of adaptation energy, a pool of available resources for the body to draw on for this general response. and he realized its value for his runners. So he tried to explain how a coach needed to monitor total stress, not just running stress, so that the runner doesn't go into exhaustion, what we would now call overtraining. It seems like a useful model, and since then most of the four-letter organizations have bought into the idea that the general adaptation syndrome is influential in our understanding of adaptation. Applying it can be problematic though. Selye would have considered strength training to be a specific defense reaction, not a general one, and that general adaptation is very different. To see why, imagine the general adaptation syndrome like a castle under siege, and a stimulus like an object hitting the wall. Most stimuli, for instance an arrow, won't penetrate, and they're manageable by the defenses, where the individual stress would be like a cannonball blowing through the wall. The alarm stage is the damage as well as the immediate full emergency response, which is chaotic, it's disruptive, it's systemic, it's inflammatory, it's all these things, but it's necessary to get repairs teams and soldiers and in the body inflammatory and repair systems online to where they're needed. The resistance stage then is like peasants trying to plug the hole back up with the rocks of the fallen wall. But since not all of the wall will be salvageable, adaptation energy and the acclimation process is like stockpiles of stone and mortar that you keep to not only repair the damage, but also reinforce that section of wall. Since after all, the enemy now has a clear bead on that point, it's important that the repair be specific to the threat. Now, in the general adaptation syndrome, the organism initially adapts to the stress and gets stronger, but repeated stresses eventually weaken and kill the organism. A dose of poison inoculates you to that poison, but with enough doses, you may seem inoculated so that it doesn't affect you, but over time, those poisons will kill you. Imagine a castle wall, it repaired for the first shot, it takes another one, and then another one, and then another one, and it doesn't matter how well they try, eventually there will be too many deep fractures and instabilities spreading too far to simply patch up. In training, if this were a correct representation, this would be like getting stronger for the first 5 years and then becoming weaker every time you went to the gym. Additionally, adaptation energy is drawn from across the organism. If I have 2 frogs, I poison one and I leave the other healthy, and then wait until the damage from the poison seems recovered, and then try to freeze them both, a very different stress. The recovered frog won't do as well. To the castle example, if you use up the supplies to reinforce one section of the wall, you're not able to fix the hole next week, or maybe, the one that comes in the next 10 minutes. If training worked this way, getting stronger would make you more susceptible to cold, illness, poisons, and other stressors. So the real question is, how is specific adaptation different from general adaptation? Understanding that, exercise physiologists developed the SRA, or SFRA, depending on where you're reading it, model. Stress, recovery, adaptation. They recognized that Selye was onto something. They loosened the definition of stress to stimulus, and they broadly applied it to training. And there's something intuitive about it. Recovery processes in this are modeled like predictive control systems. There's a built-in overshoot above the initial baseline of performance that's designed to increase capacity. You probably remember from, you've heard somewhere the model that, the muscle doesn't like hurting that much. And so it gets bigger so that it doesn't experience that kind of damage again. So essentially, one way you can think about it is like a trampoline. Some effort is put in, it depresses performance, just like you depress the trampoline, you press it down. The recovery system, springs in the trampoline's case, responds with that force, enough to raise the lifter to a new height. And from the new height, the lifter then can add more force, further causing decreases in immediate performance, but causing rebound in performance to a new height and a new height and a new height. This model appropriately captures a lot of useful phenomena in training. The first is specificity. If I want to get as strong as I can, if I want to jump as high as I can, I have to jump at the exact center of the trampoline, where my effort will produce the most height and where the springs of the trampoline are best capable of responding. So if we're aiming for general strength, the ability to produce maximal force in a variety of useful tasks, we get the best immediate results by training large amounts of muscle mass at low rep ranges that require that strength. If you want leg strength, you don't get there with curls. It's not specific enough to the muscles involved. And if you want to win the Tour de France, there's no substitute for getting on a bike for long distances because the energy system needs to be specific to that task. The second principle is progressive overload. The amount of force you have to put into the trampoline has to increase over time. If you keep up the same downward force, like you see here in the picture, the first application of force raises the jumper on the trampoline, but eventually if they keep applying the same amount of force, they don't get any higher, like the change from the second to third picture. In the same way, the total training stimulus has to increase, or you'll stop getting stronger. Progressive overload explains the first half of what we call the novice effect. A lifter will rapidly acquire initial adaptations anytime they get started, especially if they're going from sedentary to newly training, or from training a completely different task, for instance, a lifelong swimmer, to training in strength. It takes very little effort to go up a whole foot on a trampoline, but on that 100th jump, trying to get as high as you can, it may take great force and perfect timing to go up even another inch. Now, there's a second part to the novice effect, which is novice transfer, it gets a little bit difficult when balancing it against specificity. In the trampoline analogy, you can think of it like when one kid jumps as high as they can, and another, sitting down on the trampoline, still picks up height as a result. Specificity here still matters. Just like the trampoline sitter will go higher if they're closer to the jumper than if they're at the edge. The closer a side effect is in energy systems and muscle used to the primary training, the more likely the novice will see transfer without specific work. This is why a previously sedentary cyclist will get stronger on a 5RM squat, and why a new strength trainee may see improvement in their pull-ups and other high-effort feats despite not training them directly, or at all. Now, all models are inaccurate or incomplete to some extent, like we talked about in week 2, and SRA is no different. For one, even at the novice level, it assumes a decrease in performance. No decrease, no rebound. But like the novice effect would suggest, virtually any stimulus, even one that doesn't cause a performance decrease, will cause improvement. This, for example, is true of steroid use, which causes strength increases in the untrained even without training. Now, were the untrained to train and use steroids, certainly there would be much more improvement. But still, without a decrease in performance, how do we understand what is going on? Second, SRA is sequential in its design. Damage has to be done, recovery systems have to bring the lifter to baseline, then the adaptation happens. But research on hypertrophy shows that muscle protein synthesis, the process of building muscle, has already started within 3 hours of even a brutal training session. And there's no way of knowing, at least according to what we've researched, how early it actually starts. They didn't start measuring 5 seconds or 20 seconds after the training bout, or 5 minutes or 1 hour. They didn't go to that fine a detail. But within 3 hours, there was already substantial growth processes happening. In addition, although the most immediate and apparent damage from a training session is passed within 2 to 3 days, in fact, there are signals of inflammation, cell damage, and depleted energy lasting up to 3 weeks after training. So you have 2 processes happening in parallel, both your damage and your growth, your recovery and adaptive processes. To explain this phenomenon, we come to the 2-factor model, also known as FIT-FAT, proposed by E.W. Bannister in 1992. Essentially, he suggests that a training stimulus signals a response in the body. Some of those responses, mostly neural, immediately improve performance, while others, like protein synthesis, begin shortly after the stimulus and slowly increase performance. These are called fitnesses, the FIT in FIT-FAT. Other factors like energy store depletion, cell damage, inflammation, central inhibition, they immediately cause decreases in performance. These are called fatigues. Fatigues decay rather quickly, while fitnesses last longer, So the end result, you combine the green line of fitnesses and the red line of fatigues, the end result of a single session is an increase in capacity, and after a short rest or after a short time has passed, an increase in total performance for some time. The combination of these two factors creates the classic SRA performance curve. So FitFat isn't a rejection of SRA, but rather anytime we have to make caveats as coaches to explain some issue with SRA, FitFat tends to resolve those or be the explanation for those caveats. An analogy here that may help is one of a sink. Imagine trying to collect as much water as you can in buckets under a sink drain. These are strange buckets in that they have small holes that very slowly lose water, like those slowly decaying fitnesses. And this involves what we would consider detraining, the loss of training gains over time. So you can't just fill and chill. You have to increase the rate of water to collection to keep up with the fact that detraining is consistently happening. And you do that by carefully managing the stimulus and recovery. So one way to do that, you collect more water by putting more water into the sink at a time. In this case, this would increase the pressure of water pushing through the drain because the water is coming from the top. But the risk here is that too much stimulus, too much water pouring into the drain, and it will overflow. What we would consider unproductive training or overtraining for an individual lifter. You can also get more water by widening the drain, equivalent to the slow process of increasing a lifter's recovery ability, or the choice to remove blockages, like poor sleep or inadequate nutrition that stall recovery. This model explains some phenomena a little better. For instance, tapering. Now, traditionally, we taper by lowering training volume and increasing intensity. For instance, before a meet on Sunday, you might have someone do their opening attempts on Monday and then a light workout on Wednesday or Thursday before they go in on Sunday. That's one tapering approach. Now, in a rigid SRA model, where they are depressing performance, recovering, and then when their performance is at its peak, you hit them again sometime within 48 to 96 hours, the appropriate taper would simply be to do a hard workout 48 to 72 hours before the meet. So in this case, you do just another training day, another heavy training day on Friday, and you'll be good to go for Sunday. In general experience, although there's many reasons that people would go to meets, and this might be appropriate for a very novice individual who just wants the experience of going to a meet without peaking or topping or interrupting their training plan, we know in general that this isn't ideal, and FitFat would explain it. By suggesting a moderate high intensity and low volume training for 1, sometimes even 2 weeks for more advanced lifters leading up to the meet, you optimize performance, since the fatigues would dissipate rapidly. Now, your fitnesses wouldn't increase much at all. Tapering is a really poor long-term training approach. You couldn't just do taper weeks and expect to get much stronger for very long. But by not increasing your fitnesses or holding them relatively constant with low-stress training, but allowing fatigue to dissipate pretty rapidly, and staying in practice with relatively high loads, the resulting performance on meet day will be higher than we would expect from a heavy training day on Friday. Now, of course, this is only a model. That's just one example. And for all that it captures, there's plenty that it fails to. For one, it's two-dimensional. So increasing strength in a particular domain of expression, so the 1RM in the case of this example, is the sole variable on the axis, on the y-axis of performance. But the interactions of different stimuli, the gains that they cause, and the fatigues that they generate would extend beyond this and complicate this picture a great deal. For instance, if you're training for strength and endurance in a particular sport at the same time. It's fair to say that no effective program design has ever come up from the model up, starting from basic principles, but rather we backtrack the results and design of known effective programs in the conditions under which they're created and in which they generally create success, to come to a better understanding of key principles. Essentially, we are taking the same black box approach that we bring in for week 2, and we are trying to reconstruct the black box of a lifter in terms of these core general principles that tend to hold. And by understanding them better, we know more and better what to do when a program doesn't work, stops working, or when we're trying to explain a phenomena that doesn't fit our experience at all. And by doing so, we're in a better position as coaches, instead of randomly throwing programs at our lifter to solve that problem, to instead make the right choice, or at least one of a selection of right choices that continues them towards their goals in a way that we can explain that we can explain and build trust with them, that they can understand the process and the journey that they're on.